All right, hello everyone. So in this video, we're going to look over how to compute the inverse of a n by n matrix using the Gaussian elimination algorithm. So how do we find the inverse of a n by n matrix using Gaussian? So the good news here is that for the last two sections, so 12.7 and 12.8, you already know all the computations to compute the inverse because it's based on the Gaussian elimination algorithm. So if you're okay with Gaussian, you're good for that section, and of course for the section after, which is like using the inverse to compute some other things. So what is the method to compute the inverse of an n by n matrix? So the first thing you do is you construct this super augmented matrix from A by putting on the left side, by putting A on the left side and and the identity matrix of size n by n on the right side of the vertical line. So you're creating this super augmented matrix A augmented by the identity matrix. And then what you do is you apply Gaussian in its full form, in the sense that you want to transform this augmented matrix, the super augmented matrix, in row reduced echelon form. So not just echelon form, but row reduced echelon form. Okay, so you want to make sure that it's in row reduced echelon form. And then what will happen? So if on the left hand side of the augmented matrix, the super augmented matrix A augmented by I, you get so if the oh my god, so if you so after you apply the Gaussian elimination algorithm, what will happen is that there's two scenarios. The first scenario is that you start with your super augmented matrix, you apply Gaussian, and then you get a new super augmented matrix where on the left side now you have the identity, and then whatever stuff that you have left on the right side, that will be the inverse of A. So if you cannot get the identity on the right side, and we'll see an example on the left side, when we'll see an example on this right away, then there's no inverse for A. And so normally what happens, and you'll see this with my first long example, so if you are doing Gaussian and at some point on the left hand side of the super augmented matrix you get a row of zeros, then A is not invertible, and you can stop. Like, you don't need to put in the row reduced echelon form because the goal is to compute the inverse. So my first example is actually not an example. We're asking you to compute the inverse of a 2 by 2. I mean, you could use the Gaussian elimination algorithm, but normally for 2 by 2, my ultimate advice is to always use the 2 by 2 formula. So if you have the inverse, you go 1 over the determinant. Of course, normally you know the determinant is not 0. And then what you do, the 4 and the 2, they swap place. So you get 2, 4 on the diagonal. And then the element on the anti-diagonal, minus 3 and 5, they just change signs. So you get 3 and minus 5. So in this case, you get 1 over 23. Multiplying the matrix 2, 4, which were like on the diagonal but swapped. So it's a review here. And then the minus 3 became a 3 and the 5 became a minus 5. So if you multiply throughout, you have your inverse. So for 2 by 2, just use the formula. Don't use this method. So it's really when you go for 3 by 3 or more, like I must confess here, for us it will be 3 by 3 only, but for 2 by 3 or bigger, the Gaussian is the way. So here we go. So our first example, this will be an example where A will not have an inverse. So by the way, normally if you are asked to compute the determinant first, if you look at this matrix and you compute the determinant, and this is a good exercise, you will see that the determinant is 0, and then you can stop. So if you compute the determinant and you get 0, you can just use that argument to say that there's no inverse. But suppose you're a lazy piece of shit and you go ahead and you try to compute the inverse. So you create the super augmented matrix A augmented by I3. So on the left side I have A, on the right side I have the identity matrix, and you start your Gaussian elimination algorithm. So here I'm lucky, top left corner is a 1. So I start my 2 eliminations. So to destroy the 3, I'm going to go row 2 is equal to row 2 minus 3 times row 1. And to destroy D minus 2, I'm going to go row 3 is equal to row 3 plus 2 times row 1. And then what you get is, of course, you get a 1, you get your zeros under, so you feel good. Now next pivot will be minus 7. You could turn it into a 1 by dividing this row by minus 7, but as you can see now on the third row, that 7 minus 2 is very similar to that minus 7 2 on the row 2. So if you destroy the the 7 with the minus 7 simply by saying that row 3 is equal to row 3 plus row 2, then what will happen? Look how beautiful this thing happened. Like now you're getting this row of zeros on the left hand side, just like the remark mentioned. So here you can stop. There's no inverse. So if you get a row of zeros on the left-hand side, no zero, or if you took the time to compute the determinant and you get 0, no inverse, you don't need to do any elimination to check that. So it's up to you, pick your poison. But normally when we're asking you to compute the inverse, there is an inverse. All right, next example where we will get an inverse. So we have our matrix A. If you compute the determinant here, you will not get 0. But I'll just start the process. So first you construct the super augmented matrix, A augmented by I3. So you see here your A matrix, and then on the right side I have my identity matrix. So if you start Gaussian, so here I have a 2 on the top right corner. I could divide by 1/2. But this will create fraction because of the 7 and the 1 here. So normally, and this is of course a star trick, and this is why I put the star here. Look at this cute star with its smiley face. Anyways, sorry. If I swap a row 2 or row 3, so here I chose row 2 with row 1, I'm going to bring a 1 upstairs. And by the way, like if you're using that trick, it's going to simplify shit. If you're not using that trick and you're just using a software online, I'll know right away because you're going to be dealing with matrices with a lot of fractions. So anyways, now I have a 1 thanks to that little star step. Now I do 2 elimination to destroy the 2 and the 1 under my pivot equal to 1 now. So row 2 will be row 2 minus 2 times row 1, and row 3 will be row 3 minus row 1. Then I get my zeros under, not changing row 1, so I can rewrite the row 1 quickly but carefully. And then of course you do your operation throughout. I'm not going to read all the operations, but when you do row 2 minus 2 times the row 1, you will get that row here. And when you do row 3 minus row 1, you will get that row here. And now you have a choice. You could turn the minus 1 into a 1, or you can do the elimination first right away. And this is what I did here. So destroying the minus 1 in row 3 by saying row 3 is equal to row 3 minus row 2. So this destroyed my minus 1 under. Now I have zeros under my first 2 pivot. Of course, my last pivot, there's nothing to destroy under. So what I've done next is I turn my last pivot because I want row reduced echelon form. Last pivot should be a minus 1, so I multiply that row by minus 1 to get this new row 3, not changing row 2 or row 1, so you can rewrite these two quickly but carefully. Now you want to do the elimination to destroy the 2 and the minus 1 here. So to destroy the 2, I'm going to say row 2 minus 2 times row 3, and to destroy the minus 1, I'm going to go row 1 plus row 3. Then you get your 1, and now it's alone in its respective column. You move to the next pivot, which is minus 1. So let's turn this into a 1 by multiplying that row by minus 1. And now what you get is a new pivot equal to 1. You just need to do an elimination for the 4. So row 1 equal to row 1 minus 4 times row 2. Babaila, it's gone. So I have my 3 pivots. They're alone in their respective column. The left hand side is the identity matrix. So this means that on the right hand side, I get my inverse for A, so minus 3, 0, 7, 0, minus 2, and 1, minus 1, minus 1. So the inverse for A is that matrix. So it's nice 3 by 3 matrix. And of course, if you want to make sure that this matrix is indeed the inverse, what you can do is do this little verification where you multiply A by A inverse, and A inverse by A. So you can see here I'm using a color coding. So my red matrix is the inverse. So if you do matrix multiplication, so A inverse times A. So I took even the time to circle the rows of the left matrix and the rows of the columns of the right matrix. And then if you do your multiplication, you're going to get the identity. And same thing as if you go with A times A inverse and do it. It's a good exercise to review multiplication. You get the identity again. So that red matrix is the inverse of this blue matrix. All right, last important section for Unit 3, how to solve square system using the inverse. So what is a square system of linear equation? Well, a square system of linear equation, the square system for a linear equation. Wow, a system of linear equation is a square system if the system has n equations of n variables. So in other words, the coefficient matrix is a square matrix. So A is a m by n matrix. And when we have square systems, if the determinant of A is not equal to 0, so this means that there's an inverse, then the square system always has a unique solution. And the proof is very straightforward. So suppose you have your system of linear equation in matrix form, so coefficient matrix times x equal to b, where b is the augmented part. What you do is you multiply on both sides of the equation by A inverse. Then what will happen on the left side is that A inverse times A will multiply each other, and this will give you the identity matrix, and the identity matrix is like 1, so the identity matrix times x will just give you x. And then meanwhile on the right side you have that square matrix A inverse that multiplies b. This gives you a matrix. Then of course you're just going to get 1. Okay, I'm overdoing it here, I'm fully aware of that. Okay, so you get 1 times x is equal to that shitty number on the right side, and then 1 times x is just x, so it's 1/5 times 2. So it's exactly the same idea here. There's really nothing new. Dividing by 5 is the equivalent in the matrix universe of multiplying by A inverse. So this is how you're going to get your solution. So to be more precise, so at 12.8.3, the method to solve a square system, or one way, of course, is first you write your square system in matrix form, AX equal to B. Then you compute the inverse, A inverse, and then you just by matrix multiplication, if you take the inverse times B, you're going to get your unique solution for X. So let's jump and do an example right away. So first example, I have a system of two equations of two unknowns, X and Y. So in matrix form, my A is 2, 4, 3 minus 5. The X vector is just a column matrix with the variables, which is X and Y. And the B vector, or the column matrix, is just 2 minus 19. So first, now we have A inverse, so it's 1 over the determinant. If you do your fish product here, you're going to get minus 22. The 2 and the 5, they change place, and you get minus 5 and 2. The 4 and 3, they change sign, so you get minus 4 and minus 3. And then if you multiply minus 5, minus 4, minus 3 by 1 over 22, you get your inverse. But actually, when you're solving it, you might as well just keep the coefficient outside. It's going to be easier to multiply. So if you're looking for your solution, it's A inverse times B, so 1 over minus 22. And then if you do your matrix multiplication, so the minus 5, minus 4, dot product with 2, minus 19. And then if you divide by minus 22, you're going to get minus 66 over 22. And then minus 3, 2, dot product with 2, 19. Over minus 22 will give you 44 over 22, which simplifies to minus 3 and 2. And that's your unique solution. So by the way, if you put minus 3 everywhere back in, and then you put 2 back in for y, you can double check that it's indeed the unique solution and it works. Now the last example, so same thing here. We want to solve the following square system using the inverse of a matrix. So here, first you write your system in matrix form. So the coefficient matrix is 3, 5, minus 2, 1, 0, 4, and 0, minus 1, 3. That's my A matrix. My X vector is X, Y, Z. My B vector is 4, minus 9, 7. So the unique solution, X, Y, Z, is the inverse of A times B. So here I'm just going to show you the actual multiplication. We're going to go over how I got A inverse in a moment. If you already understood how to compute the inverse, you can probably just stop the video after, but I'll go over quickly the operations to get to the inverse. So anyway, so A inverse, I got it from the method of computing the inverse using the Gaussian elimination algorithm, but once you have it, coming from below here, I'll do that in a second. Then the inverse of that A matrix, so the matrix 3, 5, minus 2, 1, 0, 4, 0, minus 1 is minus 4, 13 minus 20 for the first row, 3 minus 9, 14 for the second row, and 1 minus 3, 5 for the last row. Then you just multiply it with the B vector, and if you do it, and look how ugly the solution is, minus 273 for X, 191 for Y, and 66, oh, so evil for Z. That's your unique solution. So matrix multiplication, A inverse times B, and then that gives you your unique solution. All right, how did I get the inverse? Again, here I'm just using the method. So if you're comfortable with this, you can stop now. But I'm just going to say very quickly, go over very quickly the steps from the Gaussian elimination algorithm. It's a very nice example. This is a very classical example that you will get on a test, that you typically get on a test. So to get the inverse, I have my matrix A here. Sorry, I have my matrix A. So I have my matrix A. I super augment it with the identity. So again here, you could use 3 as the first pivot, and if you're turning it into a 1, you'll have to divide by 3, and this is going to suck because you're going to get some fraction. So I'm going to use my star step. Oh, that little guy is so cute. Which is swapping 2 rows. I see a 1 below. I do a swap between row 1 and row 2. So row 2 is now row 1, row 2 is the former row 3, and then row 1, and row 3 is just row 3. Now I have my 1 for my pivot. I need to destroy the 3. The elimination is, of course, going to be row 2 is equal to row 2 minus 3 times row 1. So I have my pivot, it's 1, zeros under, bye-bye là. So I did not change row 1. I can rewrite it quickly but carefully. I did not change row 3, so you can write it quickly but carefully. But you need to do the full operation to get row 2 by subtracting 3 times row 1, and you'll get 0, 5, minus 14, 1, and minus 3. Now you move on to the next pivot. I have a 5 here. No, you could divide by 5, but this would create fraction. So no, but here I have my eyes on the minus 1. So I'm using another star operation. Look at this magical creature. So again here, the star operations are like the operations that just helps your lives, not really Gaussian. If you're using an online calculator to compute the row-reduced social form of A augmented by I, you will have a hard time writing all the steps down. Like, you need to master that trick. There's a reason why that star is so cute. Anyways, so let's swap row 2 and row 3. So row 2 goes down to row 3. Row 3 goes up to row 2. Row 1 was unchanged. Now I have a minus 1 to work with. You destroy the 5. You could multiply by minus 1 and then eliminate. Here I decided to do the elimination first. So row 3 will be row 3 plus 5 times row 2. So bye-bye. Okay, so we have a 0 under. So I did not change row 1, did not change row 2. I get my row 3 by saying row 3 plus 5 times row 2, and you will get 0, 0, 1, 1 minus 3, 5. So look at this magical moment. I already have a 1 here. So let's do the 2 elimination needed to make it alone in its column by eliminating the 3 and the 4. So row 1 will be row 1 minus 4 times row 3. Row 2 will be row 2 minus 3 times row 3. Then bye-bye, I have my 1, my freshly computed 0. Not changing row 3, so I can rewrite it quickly but carefully. And by the way, because of those 2 zeros, you can actually rewrite the first 2 columns very quickly and carefully without changing it. That's the point of doing elimination first from left to right and then from right to left. You'll be working with zeros, and you're going to minimize the number of operations needed to get to the row reduced echelon form. Anyways, so you compute your new row 2, you compute your new row 1. I just wrote the answers here. Make sure that you do the computation on your own. So now I move to the next pivot, the minus 1 here. So I turn it into a 1 by multiplying it by minus 1. And then, beautiful moment, you get your identity matrix on the left side. So what you get now on the right side is the inverse. Minus 4, 13 minus 20, 3 minus 9, 14, and 1 minus 3, 5. And that's the matrix I use to compute the unique solution, A inverse times B. And again here, it's good exercise for checking that what we're computing is actually the inverse. So if you multiply A by A inverse or A inverse times A, so this is a multiplication exercise, so it's good if you're learning how to multiply matrices. This is a good way to review this. So when you go and you do A, let me just put a smaller thing. So when you go A times A inverse, my God, you go A, so that's A here times A inverse, you're going to get the identity matrix. So matrix filled with zeros, except I have one on the diagonal, or if I go A inverse times A and do it as a matrix, I took the time to circle the rows on the left side and the columns on the right side. You do your dot product and you're going to get again your identity matrix. So beautiful moment when you multiply A by A inverse or vice versa, you get the identity for both multiplication, so you know that what you've done is correct. So again here in a nutshell, computing the inverse of a matrix, it's just an application of the Gaussian elimination algorithm. So you take A, you super augment it with the identity, Gaussian down full force, you will get on the left side the identity matrix, if it's invertible of course, and then on the right side you have the inverse. And if you have a square system, one way to solve it is take the coefficient matrix, compute the inverse, and then your unique solution is simply obtained by matrix multiplication, A inverse times B. And that's it. Bye-bye, là.